we're going to talk about another solution concept, which is called rationalizability. And let us first start with the motivation. So Nash equilibria, which I guess that's the most famous solution concept in non-cooperative games, so the games we have been studying, they have a lot of so-called epistemic requirements. Epistemic means about knowledge, and that is studied in detail in epistemic game theory, which studies what we know, which assumptions about knowledge we need to have. Here we are going to have a little bit of a taste of that branch of game theory. It is, by the way, going to be a bit harder than maybe another lecture in the technical sense, only a little bit, it's not hard. But if you feel like the technical part is too much, try to understand the intuition and the main notions. I will always stress the intuition, not only the technical part, so you will have definitely enough intuition. But I hope you will understand the technical part as well. Anyhow, if you want, you can go to the book by Osborne and Rubinstein. I follow that book. I follow the fourth chapter of that book on the for this lecture. But I hope that the lectures are even more even more accessible than the book. Yes. So Nash equilibria have this extreme requirements from the point of view of the epistemics, and that they require that everyone best responds to a belief about what others do, and the belief has to be correct. So I have to actually know what the others actually do, and that's too much. So of course, if we play a repeated game, this can be natural that I know already from experience what the others do. But if we have a one-shot game, then the epistemic assumptions are too strong. The epistemic assumptions that I know exactly what the others do, that I have a correct belief. I don't, not do I only best respond to my belief, but I also have a correct belief. So let us look at another solution concept, which is called rationalizability. And of course, I will define it soon. But the idea is that you here only require best responding, so maximizing your utility, relatively to any belief which is rational. So, assuming that others, you believe that others act in a way which is rational for them. And that means that they best respond to their beliefs, which in turn are also rational. And that is indefinitely nested. So everyone is rational, thinks that everyone else is rational, and so on. But what I think about John does not have to be the same as what another player, Jane, thinks about John. Moreover, I can think about John something that is based on what John thinks about me, and that does not have to correspond to what I actually do. So we don't have this idea that, like in the Nash equilibrium, that everyone exactly knows what the others do. But we only have that you need to think that everyone is rational, and thinking that everyone is rational, and thinking that everyone is thinking that everyone is rational, and so on. You only have the rationality, indefinitely deep rationality. No assumption about actual knowledge. Therefore, it's much more reasonable from the point of view of epistemic game theory. And it's, of course, strictly wider than Nash equilibria in general. Now, that can be exactly like the Nash equilibria, but usually it will be strictly wider, because Nash equilibria assumes the same, but it actually assumes that all the beliefs are actually exactly what the players do. And in reality, this idea that you think what others can think, which is called theory of mind, you have a theory of what others do, is in reality often limited. So actual people can think of what others do, what others think about what others do, but the levels of nesting, they're usually limited to like 3 or 4. Maybe if you have a chess master, then it will be deeper, but it's not indefinitely long. So even our assumption here, which is weaker than the assumption of a Nash equilibrium, is too strong. It's reasonable that we know the information, but it requires too much thought on our point, on the part of the player. So it's also not the real thing. Okay, so how do we find the results in this indefinitely nested theory of mine? So we are going to work on that now. And as I said, it's a little bit of a flavor of this epistemic game theory, which explicitly deals with beliefs. Like in Nash equilibrium, we also assume that you maximize your utility relatively to what you think others do, and what you think is actually what they do. But we didn't kind of delve into that. But here we are going to explicitly consider beliefs and define all the things explicitly. And we are going to prove a very simple and maybe surprising connection to eliminating dominated strategy, to this iterated elimination of strictly dominated strategies. And therefore prove that this idea of rationalizability is actually very, very reasonable. It has several ways it can be backed up, and it in turn backs up the idea of iterated elimination of dominant strategy. So to sum up, we are going to look at more reasonable assumptions than the Nash equilibria used, and this is rationalizability. This is a little bit of this domain of epistemic game theory, and they're going to connect this to iterated elimination of dominant strategies. So let us first define belief. A belief of player I is simply a probability measure on the other strategy. So what I think about what others have to do, and of course, not of course, but by definition, we allow for dependency between what others do. As we will exemplify, if we require independence, and there are models in the literature which do that, then we would have other results. So in general, this matters that we do allow dependency. But allowing dependence is also something reasonable, because in real life, why should they not be dependent? But in the notion of a mixed Nash equilibrium, we assume independent randomization. So we can think of independence. But we're going to always think of dependencies here. That, let's say so, that the probability measure on the other players does not have to be independent. It can be, as a particular case, but it can be anything. And being rational means that you just best respond to whatever you believe about others. The thing is that what you believe about others, unlike what we did in Nash equilibrium, does not have to be what they actually do. And there is no requirement what I believe about John coincides with what I believe that John believes about what Jane believes about John, or what I believe that Helmut believes about John. So the definition is the following: that given a strategic form game, a strategy of a given player is rationalizable if all the following exist. And T denotes time or depth. So we need to have a sequence of sets of strategies, and they will be the rationalizable sets. So the strategies at depth T of player J. So the fact that Si is rationalizable is going to be justified by the belief mu I mu1, excuse me, mu1, so at the first indirection step of player I, and that belief will be the belief with respect to which we will require that Si is the best response. And everything, every S minus I, which has a positive weight in this belief, which can happen with a positive probability, has to be in x1 minus I. That's the role of those sets. There are sets that are required to assume for our beliefs. So we have a belief hierarchy, and that's a bit confusing, but not hard. So Si is justified because there is a belief mu1 of I, which has its support inside xi minus I, and everything there will have a justifying belief too, and so on indefinitely. So everything for any player and for any depth t, any strategy j in xtj is also justified by some belief on the next level, mu t plus 1j, and for any such as j, there in general is another maybe a proprietary belief mu t plus 1j of sj, that its support is in the next set in x t plus first level of indirection of minus I. So the intuition is that the sets of these sets, sequence of sets, are those sets of the strategies which are required for us, and for the justification of what we assume that Si is rationalizable. Si concretely justified by the belief mu I1, but mu I1 requires some belief on the other agents in in xy1 minus I, and each one of them requires some belief. Each sj there in xtj requires some belief in the next level, mu t plus 1j of sj, and that belief is a probability distribution on the next level, such that every strategy which can happen with a probability belongs to x of the next level. So those sets and those beliefs is a system which indefinitely long allows me to base the original assumption, the original statement that Si is rationalizable. Okay, so you have this sequence of set, and then the full definition. So now this was the first part, and now the requirements, which I already hinted at, are as follows: that Si itself is the best response to this belief mu1I. Now x1I is empty because the belief of I is over other players, but for any other j other than I, x1j is exactly those who are used in at least some profile of the other players, having a positive weight under mu1I. So those sj primes, who are used in some sj having a positive weight. So exactly those who are used. Now we are going to also define that at any level, the sj at any, so every member of xtj is in turn its kind of a recursive definition, is in turn a best response, not necessarily the only one, to some belief mu t plus jth level. Excuse me. I press on the slides and the slides go forward. So it's a best response to some belief which has its support in the next level. So the definition of xcj, the actions of j which we need at time t, are all the s primes in sj that can be used in some sj, which is a strategy profile which has a positive weight. So let me just kind of quickly recapitulate, because it's not hard, but it just defines, it's a bit confusing because it defines a hierarchy of beliefs with respect to which everyone is optimal. So this equivalence set, which we are going to need in order to talk about which strategy is optimal. The belief which justifies the origin, the SI, which we define its rationalizability, is called mu 1, so a time t of I, and we require the support of that belief will be in x1 minus I, so that x1 minus I is big enough to support this belief. And now every member of x1 minus I needs a support too, needs a belief to which it's the best response, and so on and so forth. So in general, for any player and any time t, any nesting level t, and any member in xtj, any member is j and xtj, it's supported by some belief, mu t plus next level t plus 1 for player j. The exact belief that supports j, it can depend on j. So everyone has this belief, supporting belief, and the strategy profiles S minus j, which are in the support of this belief, so which has a positive probability according to mu t plus 1j. Those strategy profiles, they have to belong to this x of the next level of t plus 1j. So we have that those x's provide this necessary support for all those beliefs. And so this is a system of beliefs and sets that support them. So everything that the beliefs give a positive probability belongs to those sets. And then the original SI, which we define as rationalizability, is optimal, is in the best response. BI denotes the best response to the belief mu 1I. X 1I exactly includes all those who are in support of mu 1I. And then on any level, the Sj, every Sj in xj is a best response to what we have in the next level. So everyone is justified by the next level, and then is justified by the next level, and so on. And in general, the members of xtj are all those who are required to justify what was in the previous level. So that there is some one in the previous level, such that its mu gives a positive weight to some s minus k, which j's element is equal to sj prime. So this is a set of a collection of sets, a sequence of sets and beliefs that fulfill the idea that fulfill the requirement that Si is the best response with respect to the original belief, and whatever that belief assumes, whatever strategies that belief gives positive probability to, are best responses in turn to the next beliefs on the next order. So everyone is optimal. I am optimal given my belief. Whatever I believe is optimal given their belief. That does not have to be the same, as I said, but there is this infinitely deep strategy, excuse me, hierarchy of beliefs. Now let me just denote that the requirement that x1j includes everything which is in the support here, x my, excuse me, that x1, yeah, minus I includes everything which is in support, and for in general x t plus 1 minus j includes everything which is in the support of what we need in the belief mu to justify the strategies of the previous level. That's necessary. But the fact that the x's are exactly only those who are here, that's redundant. So we can just remove that and that, the second and the fourth conditions after the such that. But that is simply simpler to leave them. And let us now draw a finite part of a belief hierarchy when we have three players. So assume that we have players I, J, and K. They are all different. Let me just say that when I said the conditions 2 and 4 are superfluous, I mean that we can allow for larger sets x, t, I, x, t, j, or x, t, I. It will simply mean that we use more possible actions which will need to justify. So it definitely does not make it easier for us. But if we want, we can justify the actions as we want, as long as everything which we use to justify a strategy is justified, in turn justified. So we don't want to use too many strategies to justify something, because we need to justify them recursively indefinitely. But we can require, it's simply something we can require, that we don't use too many strategies to justify something. But if we want, we are free to use too many strategies. So now we have belief hierarchy, an example of belief hierarchy for two actions. Excuse me, for two players I, J, and K. So we justify the action as I of player I by some distribution on the actions of other players, which as I said can be coordinated. And every action is as xij is justified by some distribution on the actions of other players, x, so x2i and x2k. Every action in x1k, one is the level of indirection, so it's the first level, is, and k is a player, is justified by the actions on the second level of indirection of the other players, so x2i and x2j. And x1i is empty, so it actually does not need anyone. Actually, those lines are redundant because it's empty. But x2j and x2k are not empty because they are needed also to x2j is not needed to justify x m members of x1I because x1I is empty, but x2j is also needed to justify members of x1k, and x2k is needed to justify members of x1j. But x1I is empty. Let me actually write this because I forgot to write it. So x1I is the only empty set here. And as I said, it theoretically goes for the justification to x2j and x2k, but since it's empty, x1i's elements don't need any justification. Now, as for other sets, none is empty since there are more than two elements. But if there were only two elements, then what are we going to have for two elements? x1i will be empty, and that means that x2j will be empty, and x3i will be again empty. So x of the odd levels of I will be empty, and x of the even levels of j will be empty. Because we begin with why can player I act according to SI, and for two players the justification is only the other player. There is, and then that will need only, so it will be only assume that there were no player k. So SI will be justified by some elements of x1j, which will need the justification of some elements of x2i, but x2j will be empty, and so on. But if there are at least three players, then the only empty set is x1i. So this denotes which sets I needed to justify the original action Si of player I. I hope you are not confused, but I give you a lot of intuition, as you noticed. So even if you are a bit confused with notation, try to grasp the intuition. That's the main part. Unfortunately, unlike in a normal math, in this lesson I allow you just to grasp the intuition. Please try to understand the notation, but at first listening you can only grasp the intuition. Because it's not hard, but it's notation-wise confusing. So the meaning of x1j for j's other than I is a set of actions that I believe j can undertake, which I needs to justify her action I. And the next level, x2j, is a set of action j such as other players than j, k, playing some sk, which we needed originally for justifying si. Now sk is justified by a distribution mu2k and if there is an sj which gets a positive probability according to the distribution, which is in the support, so to speak, then this sj needs to belong to sx to j. So we see whom we need to justify. Of course, sometimes we cannot justify. In this case, the whole structure is wrong, and the original action is I is not. If we cannot build the strategy, build this structure with justified, indefinitely long nested justified actions, or actions, I mean strategies, then it means that the original action as the original strategy Si is not rationalizable, because all this is the definition of what it means for Si to be rationalizable. Okay, let us now look at an example which I hope will help you with the intuition. So consider the game of 3 players, and the strategies of those players are A and B, 2 options for everyone. And there are utilities which I don't define now, but I assume that as I don't define the game completely and just give you some examples of notation. So I assume that A, action A in SI, is rationalizable by some probability distribution mu1 of 1. So the upper one is the nesting level, and the lower one is the player for which we do it. So action A is rationalizable by this distribution, and assume that this distribution gives positive probability to the following actions of players 2 and 3, AA and BB. That requires that sets x1 of 2 and of 3 include A and B, because every player can sometimes play A and sometimes play B. Assume that the beliefs that justify actions A of player 2 and actions B of player 2 justify means that action A is a best response from the point of view of player 2 to this belief u22 of A, and the action B is the best response from the point of view of player 2 to the belief u22 of B. So those beliefs justify. They have to be distributions. I just basically give you an example of whatever I told you on the actions of other players. So it's player 2, so the distributions are on S1 and S3. It can depend. It can say that only this combination of S1 and S3 is possible. It does not. We don't require that the distributions are independent on S1 and S3. And the analogously, the distributions of the belief will justify A and B of player 3. So the beliefs such that A is the best response from the point of view of player 3, and B is the best response from the point of view of player 3. There are distributions on the strategies of other players, so 1 and 2. And unlike in that equilibrium, when everyone has eventually the same belief, which is true, what actually the players do, here in the belief which justifies action A of player 2, belief that justifies action B of player 2, belief that justifies action A of player 3, and belief that justifies action B of player 3, everything on the direction level of 2. That's what we look at. Those do not have to coincide on what they predict for player 1. They don't have to contain in the action A, which we began with, which is rationalizable, and the structure for which rationalization we are building, they don't have to contain this action as an action of player 1 in the support. So player 1 can rationally act according to some belief, which believes eventually is based on some belief which does not assume that player 1 acts like that. It's only required that at any stage, what I do is the best response with respect to the next stage of nesting, and what the next stage does is also a best response with respect to some other stage of nesting, and it can go infinitely long. And now x to 1 is exactly those strategies of player 1 which I assign positive probability by those distributions on the other players. So the distribution on player of the player 2, which justifies the strategy A of player 2, the distribution which justifies the strategy B of player 2, the distribution which justifies strategy A of player 3, and the distribution which justifies strategy B of player 3. So all the strategies which do appear in x1, 2, and x1, 3, which are A and B, they need to be justified, and the probability distributions of the beliefs which justifies them have their supports in x21. And also we also note that all this was for some utility functions for which these not even well-defined, not even fully, but not fully defined probabilities, they justified our actions in the sense that the actions were best responses. Of course, if we had another utility function, then those sets could have differed, but only x11 will be empty. Why only? Well, x11 will be empty because in order to justify the strategy of player I, x1I will be empty because that player I only looks at other players in order to justify her strategy. But since I do need to look at other players and there is some probability to distribute, then I need to have some strategy profiles on the other players. So the other some strategy profiles which have non-negative probability, positive probability. So the only x2 the only x1 which is empty is x1I, and of course the other x1, 2, and x3 they don't have to be A and B, but they will not be empty. And to justify them, we will need already x2, 1, 2, and 3, all of which will be non-empty, and so on. So the only set which is empty, because we have at least 3 players, is x1I. Okay. Now, let us look at another definition of rationalizability, which we will show to be equivalent to the first one, but it's a bit simpler, because in the first definition, we actually built the structure of sets and distributions on those sets with respect to which distributions the actions were best responses. So we justified the action of starting with the action which we say is rationalizable of some player I, then looked at which actions we need for that distribution on other players to justify that, which actions we need to justify in turn those, and so on and so forth. So we looked at justifying someone by justifying someone else by justifying someone else, and that was this hierarchy which we explicitly defined. Now we can also look at this in a simpler manner, and that's the following. Given a game, strategy Si of player I is rationalizable if there is excuse me, for any player we have a subset of strategies Zj such that Si, those J's will be the rationalizable ones. So Si will be in Zj, and anything in Zj has some distribution such that Sj is a best response to the distribution, and the support of the distribution is, or of course I wanted to say, in Z minus J. Yeah, let me fix that. Another definition. So, given a game, I want to define this thing from another direction. Look at the strategy. For every player, you have ZJs, which are subsets of the strategies of that player. It can be all the strategies, but it can be in general some subset. It will never be empty, but that will follow later. We don't know yet that they will never be empty. Such that everything, every strategy J in ZJ has some probability distribution such that Sj is the best response relative to that probability distribution. So that, in other words, that probability justifies Sj. And the support of that probability is in Z minus J. So everything in Zj is justified using the others Zj's. So the system of sets Z1 till Zn justifies itself. And there is no need to build something in infinite in this definition. And Si belongs to Zi. Now, please notice that in this simpler than, I think, previous definition. So it's not clear immediately why they're equivalent, but we will prove it. If you have a system Zj of rationalizable actions, because the definition, of course, is good for anything in any Zj, so we just have this property 2, that any action in Zj is justified by some distribution over other Zj's, and then we can, that already tells us that any action in Zj is rationalizable. So those are basically already sets of rationalizable action. And if we have one such n tuple of Zj's for every player, and some other n tuple of Z prime J's that satisfy the definition, then it's of course true that the n tuple which is formed by uniting Zj with Z prime J for any player. And it's everything says the definition. Because in order to justify anything in this new set, we will look, okay, where is that Sj which we've taken? It's either in one or in another Zj. It's either in the J, excuse me, or in the J prime. Maybe in both, but then we just take any. And any of them, in any of them, we have this just defined distribution mu j is j, which has support in the other j's, in particular in the union. So by the definition, the n tuple formed by uniting Zj with Z prime J is also an n tuple which satisfies the definition. Therefore, it's reasonable to look at, okay, what are the rationalizable profiles? Those are all the profiles that can be defined all the profiles which are contained in the largest Cartesian product of such J's. There is the largest because if that's not the largest, then we can just unite several sets till we cannot extend those. So that's another way to speak about the set of rationalizable set of rationalizable actions. We can simply say that those are all actions which are rationalizable according to this definition. But we also can say that that's also representable as the Cartesian product, which is the largest. And now let us prove that the two definitions are equivalent. So the intuition of the direction that if we have the first definition, which have this, which had this infinite infinite hierarchy of beliefs, that then we can simply flatten it, or to be exact, unite it to the second definition. And despite that the first definition is extremely hairy with a lot of details and infinitely many sets, maybe not differentness sometimes, but maybe different sets, then still we can combine it to the second definition where we have only zj's for any player. And the idea is that those j's can simply be the unions, so that they aggregate the multi-story, metaphorically speaking, hierarchy of xtj's. The stories are the t's, the nesting levels, which we had in the first definition. So we just unite them all and thereby flatten that. And the beliefs, which could be different at any t, just we can choose any belief as long as that belief justifies the strategy. And that's good enough for us. So let us assume that the first definition holds, and let us prove that we also can prove that the strategy Sj is also, which we assume is rationalizable according to the first definition, is also rationalizable according to the second definition. So we define the Zj to be the union of Si and then all the strategies of the player I that we needed on the way, all the infinitely many sets, different or not, and that J for any other player J also, it's the union of all those sets that we needed to justify other actions. Now, by definition, Si isn't in J. Now, we now prove that the requirements of the second definition hold for that set of J's. Now, for any Sj in the J, since the J is defined as this union, Sj is either Si or it's in Stj for some t, for some nesting level. That's because how these Zj's are defined. Now, if Sj is I, then since we know that Si is a best response, which spoke to this mu1i, so is Sj, which is equal, we assume. And since mu1i is a support, which is a subset of x1 minus I, it's also a subset of z minus I by the definition of z minus I, because it's a union. So that works. We can justify as this kind of Sj, which is equal to Si, in the new system of the J's. Otherwise, so there is some t which gives us that Sj is in the x, excuse me, t at the level of j. Then Sj by the definition of by the first definition is the best response to some mu tj mu j of Sj. This mu can depend on the t and so on. And the support of this mu t plus 1 j Sj is in xt plus 1 minus j, which is by definition of zj, z minus j there. So we may take any t, given that Sj, we can just fix any t. Take that mu, that justifying distribution, it will be in z minus j, so it will be fine. And thereby, we also managed to justify any Sj, which is just in xtj. So we assume the first definition, and we've built ZJs and showed that we can choose probability distributions mu such that the second definition will hold, and the second definition will also will state that S that this Si is rationalizable with respect to the second definition. Now, let us look at the other direction, the intuition for that direction. So we assume that we have these ZJs, and we need to define this hierarchy, indefinitely long hierarchy of that the originally rationalizable action is justified by the actions of others, and so on and so forth. So how do we define this? We just define this hierarchy based on the justifying beliefs which we are given. Simply we just inductively define that. So to be exact, we assume the second definition and let us the mu 1I, the probability distribution which justifies this action, which we claim is rationalizable, be the mu I Si, the one which justifies Si. And at any further in direction level, nesting level, the mu T, mu of level T, which justifies Sj, be just mu that justifies J. It's going to be the same for all the levels. By the assumption that mu J, J that justifies Aj, I want to say Sj, not Aj. So let me fix that. By this assumption, these probabilities also justify the actions. And now the sets, the infinitely many sets xtj as defined as in part 2 and 4 of the first definition. So all the actions which are required for the support of those distributions. And then the conditions from parts 1 and 3 hold. So the first definition holds, assuming the second definition. Let's now quickly go back to the definition so that we remind what happened. So the first definition has this hierarchy of x's as mu's, and then we can say exactly what is x1j and xtj. So that's how we define those x's. And then si is the best response from i's point of view to mu 1i, and NESJ is the best response from j's point of view to mu at the level of t plus 1 of j. So that is what we get because we assumed this another definition. So now let us provide a small example for rationalizability, for which we have already given two equivalent definitions. And the example is as follows: that sometimes rationalizability yields crisp results, and when can this happen? When we have, let's say, Prisoner's Dilemma or any other game which has a strict dominating equilibrium. So a profile of strategies who are strict dominating, which is not something we often have, but if that is, then the dominant profile is the only rationalizable profile. It is a rationalizable profile, it's the only rationalizable profile. Why? By the way, when I don't show you the whole slide, it's usually because I want you to think. So you may stop the video and think, and then go to check what you thought about. That's what you always can do, of course, to practice your thinking and understanding. So a dominant profile is the only rationalizable one, since the dominant profile is the only best response strategy. And that's why it is a rationalizable profile, and it's the only rationalizable one. But in some cases, the results of our rationalizability definition can be weak. For example, sometimes they don't constrain the profiles which are rationalizable at all. Look at the pure coordination game, so that you have top, bottom, and left, right. Here we have two Nash equilibria. One is top left, another one is bottom right. And therefore, the and therefore, okay, I've missed that. My apologies. Okay, let me go back to one slide. So after having proved that definitions are equivalent, we make a simple observation that if a game is finite, then if you have a mixed strategy Nash equilibrium such that Si is in its support, so Si has a positive probability in this mixed strategy Nash equilibrium, then Si is rationalizable. So any strategy which is in the support of a mixed strategy Nash equilibrium is rationalizable. And simply look at the ZJs to be their support. And then, since any action in support of a mixed Nash equilibrium is by a lemma we proved once a best response to all the others, then the second definition is fulfilled. So any strategy in the support and strategy in such as ZJ is the best response to all the other strategies, which are in others J's, and therefore the second definition is fulfilled, and Sj is rationalizable. I remind you what the second definition is. So anything in N is a J has a probability distribution over the others with respect to which this Sj is the best response, and this probability distribution has to be such that support is in the others J's. So if you have a mixed Nash equilibrium, then everything in support is rationalizable. And therefore, going to the example of a pure coordination, since we have two mixed Nash equilibria, two pure equilibria, which are in particular Nash, we also have others, but at least two. Those are enough. One is top left, another one is bottom right. Any pure strategy is in the support of some equilibrium, and therefore, by the observation, all the strategies are rationalizable. So in this case, it is extremely weak. Now, let us look at another more interesting example from Osborne and Rubinstein. So we have 4 strategies for one player, 4 strategies for 2 players, for the other player, and we want to find all the rationalizable strategies. So first, we notice that strictly dominant strategy cannot be the best response, and therefore it cannot be rationalizable. Because rationalizability requires something to be, in particular, a best response. Now, therefore, we may delete strictly dominated strategies because it cannot be rationalizable, and it cannot be rationalizable at any level. So it cannot be used at our definition because all strategies we use in our definitions has to be best responses. So we may delete strictly dominated strategies. So first B4 is a strictly dominated strategy by the mixed strategy 3, 5, B1 plus 2, 5, B2. So we may delete B4, this one, and result in that. Now we have that A4 is strictly dominated by the mixed strategy which takes half A2 and half A3. So we may delete A4, resulting in the following game. Here, no strategy is strictly dominated. So what do we do? So now we claim that every strategy in this game, so A1 and 2 and 3 and B1, B2, B3, is already rationalizable. We have proven that no other strategy here is rationalizable, but how do we know that every strategy here is rationalizable? So in the future, we'll prove that the rationalizable strategies are exactly those who survive this iterated deletion. Aha.